You ever see one of those massive container ships just gliding across the ocean? And you wonder, what does it take to power an engine that's as big as a building? Well, it all comes down to its lifeblood, the fuel. But this stuff, it isn't just a simple liquid. Oh no. It's a complex chemical cocktail with like a dozen different personalities. So let's get into it. Now, I want to be really clear from the get-go. Everything we're about to unpack in this explainer, it's all built on the incredible and comprehensive work done by Dr. Samith Tawfik. He really laid out the science behind marine fuel systems. So here's our roadmap. We're going to kick things off with the basics. Then we'll dig into the fuel's physical properties, how it actually behaves as a liquid. After that, we'll look at combustion, how it makes all that power. Then we've got to face the music and talk about the hidden dangers, contaminants, and we'll wrap it all up by looking at the incredible balancing act an engineer has to perform every single day. All right, first things first, let's talk about how this fuel actually behaves as a physical liquid. This is all about its weight and its ability to move through the very veins of the ship, all those pipes and pumps. It really all starts with a density. In the simplest terms, density is just how heavy the fuel is for the space it takes up. Think of it as its heft. Is it a feather or is it a bowling ball? So, why do engineers obsess over this number? Well, for starters, fuel is bought and sold by weight, not volume. So you need the density to know if you got what you paid for. But here's the really crucial part. It's essential for setting up the purifiers. These are machines that spin the fuel at crazy speeds to fling out water and gunk. If you get the density setting wrong on that machine, you could be sending a slug of water straight into your engine. That's a bad day. The purifier needs to know the fuel's weight relative to water, what we call specific gravity, to do its job right. Okay, next up is viscosity. Now, if density is about weight, viscosity is all about flow. It's basically a measure of how thick or syrupy the fuel is. And heavy fuel oil at room temperature, it can be like tar, almost a solid. And this is exactly why engineers are constantly checking the viscosity. If it's too thick, you can't even pump it from the tanks. But even more important is what happens right at the engine. The fuel injector needs to spray a super fine mist into the cylinder to get a good burn. If the fuel is too thick, you don't get a mist, you get little dribbles, and dribbles don't burn well. The solution? Heat. We have to heat this fuel, sometimes way up over 130 degrees Celsius, just to get the viscosity thin enough to work. And speaking of temperature, that leads us right to the pour point. This is the absolute coldest that fuel can get and still, pour. You go just 1 degree below this temperature, and the waxy parts in the fuel start to crystallize and lock up. It turns into this thick, unpumpable gel. So just imagine your ship is sailing through the North Atlantic in winter. If the fuel in your storage tanks drops below its pour point, you are in serious trouble. The fuel won't flow, the pumps will starve, and your main engine will just stop. This is exactly why those massive fuel tanks and long pipelines are wrapped in heating coils, to keep that fuel warm and flowing no matter how cold it gets outside. All right, so we've managed to get the fuel from the tank all the way to the engine. Now for the exciting part. Let's talk about what happens inside that engine cylinder. This is where the magic happens. This is combustion. This is where we unlock all that power. But hold on. Before we get to all that power, we absolutely have to talk about safety. And that's where Flashpoint comes in. This has nothing to do with how well the fuel burns. It's all about how easily it could catch fire by accident. It's the temperature where the fuel starts giving off enough vapor that a stray spark could ignite it. And here it is. The magic number for maritime safety? 65 degrees Celsius. For a fuel to be considered safe enough to store in a ship's main tanks, international rules say its flashpoint must be above 65 degrees Celsius. Anything lower is just too volatile, too dangerous to have sitting in huge quantities on board a ship. Okay, now for the good stuff. Calorific value. This right here is the single most important measure of how much energy is packed into the fuel. To put it simply, it tells you how much bang you get for your buck, how much heat you can get out of it when you burn it. And why is that so important? Well, the entire point of an engine is to turn that heat energy into mechanical work, to push that massive piston down, turn the crankshaft, and spin the propeller. So a fuel with a higher calorific value is just more efficient. You get more power from every single drop you burn. But just having a lot of potential energy isn't the whole story. That energy has to be released in a very controlled way. That's where ignition quality comes in. Big diesel engines don't have spark plugs. They use immense pressure and temperature to make the fuel ignite all by itself. Ignition quality, which we measure with a cetane number, tells you how quickly and smoothly the fuel will do that. See, if the ignition quality is poor, the fuel kind of hesitates for a split second before it lights up. And in that delay, too much fuel gets injected. So when it finally does ignite, it's not a smooth push, it's an uncontrolled explosion. It's something we call diesel knock. And that shockwave is like hitting the piston with a sledgehammer from the inside, incredibly damaging. Good ignition quality gives you a firm, powerful, and smooth push, and that's exactly what you want. So we've covered how fuel should behave and how it should burn in a perfect world. But here's the catch. Marine fuel, especially the heavy stuff, is literally the bottom of the barrel sludge from the oil refining process. It is far from pure. So what happens when you throw all these nasty contaminants into this super finely tuned system? And that brings us to maybe the single biggest headache in marine engineering, dealing with all the hidden dangers that are lurking right inside the fuel itself. These are the impurities, the unwanted passengers, that can absolutely wreck an engine if you don't manage them. Think of these as the four horsemen of engine trouble. You've got ash, which comes from metals like vanadium, and it forms this nasty, corrosive gunk at high temperatures. There's water, which causes rust everywhere and can blow the tips off your injectors. Then you have sulfur, which turns into sulfuric acid, eating away at your engine parts from the inside and causing acid rain. And finally, carbon residue, which bakes into hard deposits that clog everything up and wear down your pistons. Every single one is a serious enemy. So when you start to put all of this together, the physical stuff like viscosity, the combustion needs, and then all these contaminants, you really start to see the huge challenge here. It's not about just one property. It's about managing all of them all at once in this constant, delicate balancing act. So what's the big takeaway here? First, fuel is an incredibly complex fluid. It's not just go juice. Second, every single one of these properties we talked about, from density to ash, has a direct impact on the ship's machinery, from the storage tanks all the way to the exhaust funnel. And at the end of the day, a marine engineer's job is this high-stakes puzzle, constantly balancing the price of the fuel against engine efficiency and the long-term health of their very expensive machinery. And that leaves us with one final thought to chew on. As the world pushes for cleaner energy and brand new kinds of fuels, things like biofuels or maybe even ammonia or hydrogen, which of these fundamental properties do you think is going to be the most critical or maybe the most challenging to get right? Because the answer to that is going to shape the next generation of engines. This entire deep dive into the seriously complex world of marine fuel oil was made possible by the foundational work of Dr. Sameh Tawfik. Thank you so much for joining us.